Okay, this video here is going to give us just some basics about how we're going to do the MPL115A2 API for the PSOC devices. So this is going to be using PSOC Creator 4.2, and we're using a PSOC 4 device. It's a 4200. And so this is the data sheet, and anytime you're going to be writing an API for any kind of sensor or peripheral, the data sheet should be the most critical thing that you should have with you. Sometimes you might want to even just have a printed copy of it to have right next to you to refer to it. That's what I prefer, or at least have two monitors, so you have it open on one monitor, and then you can have your code open on the other one. Now, it gives a general description of this component here, but we're going to go ahead and go through this data sheet. Now, when you read data sheets, the key thing to remember is it's not like reading a book. It's not even reading like a textbook or anything like that. You're going to have to read this multiple times to be able to understand it. In fact, sometimes the first time you read through a data sheet, you might understand nothing. And so then you have to read through it again and read through it slower, and then really read through it by sections so that you can really understand it. And I'll illustrate that here in a moment. But we have our general description of this device. So it measures pressure and then temperature as well. It has some of the features here. It's good to read through some of these because there's something very important right here that we know we're going to need for an I2C interface, and it's got the device address 60H. Now this particular device has a fixed address, so we wouldn't be able to have multiple devices on the same I2C bus. Now if you needed multiple devices on the same I2C bus, this is where you'd have to then contact the manufacturer and see if there's any way to have for the MPL115A2, if there's any way to manufacture the 7-bit I2C with different addresses. Now in reality they might be able to do that, but in reality they're not going to do that unless you're talking about large bulk orders, or if you're talking about small scale, you're going to pay through the nose for it. Gives some applications, that's great. Gives us some ordering information, ordering options, so tray or tape and reel, and that basically, tray or tape and reel really just have to do with how they're packaged so that a machine can assemble them, like a chip mounting machine, a machine that will place all the surface mounting components. Actually really cool machines to look at. Then this first one gives us a block diagram of what's going on here, so we can kind of see what's going on, and you can look through here and see, and we can say, oh look, I've got the I2C interface, I've got the SDA and SCL. Now this is the data sheet for the chip, and so it's saying that, hey, wait a minute, you need to put 4.7 k ohm resistors here, tie-ups, and then you also need to have 1 microfarad and a 1 microfarad capacitor here between VDD and ground, and then also there's a cap here of 1 microfarad, and we can probably see why we need a 1 microfarad cap here under the cap one if we look more in our data sheet. This capacitor here though is more for a power cap. You'll often notice that you'll put like a 1 microfarad in parallel with the power supply or something, or even a 0.1 microfarad. Lots of chips or ICs require that, and that's just to make sure that any kind of power demands that the chip might have, it can meet those power demands, meaning if it needs a lot of charge at a particular moment in time, this capacitor will be charged up and it can just kind of pull it from this capacitor. Alright, and then of course it's got the pin diagram, and then power supply, and it gives us the range of the power supply, so we have a various range of input voltages we can use. Cap, it just says 1 microfarad connected to ground, so we just need a 1 microfarad capacitor for the device, and of course 1 microfarad would not be a feasible capacitor to put on an IC. Capacitors in general are difficult to put on ICs. And then we of course got some other things, ground pin, shutdown, and it says, okay, wait, let's look at this one here, connect to ground to disable the device. And when it's shut down, the power draw is no more than 1 microamp of supply current, and all communications lines are in high impedance. and then it says connect to VDD for normal operations. So that's kind of an important pin we could play with, because that would enable us to, if you're talking about wanting to make sure you don't do battery drains for an actual real application, we can shut this down, because if you think about 1 microamp, even at 5 volts, or 5.5, 1 microamp would be 5.5 microwatts, so it's not going to be consuming a lot of power in the shutdown mode. It's got some handling information, it's got some board mounting recommendations. Oh, here we finally get to some functional descriptions. Sequence flow chart. So it says initial power up, which of course just means you're connecting power to the device. Reading coefficient data. Okay, well that's going to kind of be the first thing we're going to have to do here, is reading coefficient data. Oh, and then it says there's a data conversion we need to do. Okay. And then we read the pressure, and then we either go back and do more readings, or we put it into that shutdown mode and move it back there. Now, the API we're going to build is going to have it not use the shutdown mode, but we will talk about adding this in later on. Okay, so initial power up, and it's just basically it's saying once power up, device enters a standby mode. And then it says here user typically reads coefficient data. Main circuits within the slave device are disabled during the read activity. It is not necessary to read the values that stored multiple times, because the coefficients within the device do not change. Now this is important though. However, note that the coefficients will be different from device to device and cannot be used for another part. So we do have to read it in like once a time. Like once the device has been powered up, we need to read the coefficients in once. Data conversion. This is the first step that is performed each time a pressure reading is required, which is initiated by the host sending the convert command. Alright, so we have a convert command. Compensated pressure. Host microcontroller reads from the ADC output register and compensated pressure, a barometric/atmospheric pressure value which is compensated for changes in temperature and pressure sensors linearity. And then this is done using coefficient data, and then raw sample pressure and temperature data is okay, compensated. Detailed later. That's good. Shutdown. For longer periods of inactivity, the user may assert the shutdown. Okay, so we already talked about that. Now, this is something you're always going to look for in a data sheet when you're trying to write your own API, and this is a device memory map. And first off, we should see here the devices here. The addresses are like 00, 01, 03, 04, 05, 06, 07, so on and so on. And it gives us a name that it calls those registers, which we'll actually use those names later on. But then it gives us a description of what's stored in there. And so we can see the pressure, and we can see MSB for most significant byte. We can see all the coefficients here. So that's really nice. And then it's also got, if we got some reserved here, and it has a little footnote 1. The register is set to 00. It is reserved and was previously utilized as coefficient values C11 and C22, which were always 00. So it's just trying to give you a note on why those are reserved, but we don't really need to know. And then it's giving for values with less than 16 bits, the lower least significant bits are 0. So it says, for example, C12 is 14 bits and is stored into 2 bytes as follows. So it gives us precisely, we've got C13 to C6 in the most significant byte, B5 to B0 and the least significant byte, and then 2 additional zeros here. We'll have to take care of that when we read the data in. Then it actually gives us more information about the actual coefficients that we're reading in and about the pressure and temperature data that we're reading in. And it gives us more information on this table. So all of this information is very critical to us. And then as we continue compensation, the 10-bit compensated pressure pcomp is computed as the follow. Oh, look, it gives us a nice formula for computing the compensated pressure. A0 B1 plus C2 TADC times BADC plus B2 times TADC. Great. And then it's got an equation for computing the pressure in kilopascals. And then it's got this like evaluation sequence, but this is just an example. It's trying to do these in like one lines at a time, which I honestly find this confusing. If I'm thinking about programming, I can just program this one equation in up here. Instead, what they did is they programmed it in many different lines, which I'm not quite sure why they did that. And then it's got read-write operations. Now, some of this device address and write bit, we don't have to worry about this too much. This is if we were to physically be sending the byte to the bus ourselves. But remember, the way the PSOC start command works for the I2C is you give it the device address and whether you want to be in read or write mode. So PSOC automatically generates this code for us. But there is something here, I2C write commands here. This start conversions. So that's important for us to notice. And then read commands, basically, again, we don't need to know anything about the read, but what it's saying is if you read pressure MSB, it automatically goes to then points to LSB, so we can actually go through there. And it tries to go through an example here just to show you here. So for instance, we write device and write bit to write, and we write, okay, that we're in write mode and we're going to write the address. Then we set it to read mode. And then this is actually to set it in write mode, to set it in read mode. This is the command to convert it, command to read in different things. Some of these commands we won't have to worry about quite as much. This is if we essentially didn't have an API for our I2C. Now what's important here though, it gives us some example numbers. That's great so that we can actually test our code to see if our numbers match up. And it gives us even a worked out example. Now there's an error in this formula. The formula we had in the previous line was correct. Now it's starting to give us some actual electrical characteristics, maximum readings, things of that, some voltage readings. Okay, typical voltage operation is 3.3, which is great because that's what our device operates at. Some other things, but some of this isn't necessarily what we need here. And then basically we get into mechanical schematic, which is of course something you need if you were making a footprint for this. So you could use this diagram right here to create a footprint so that you could actually assemble PC boards for this. And then this is just showing how it's packaged. And then soldering, it's telling you basically what kind of solder you should use for it or what's recommended. And if you're talking about soldering these by hand, well, one, it would be very difficult because of the pad location. It's not impossible, but it would be very difficult because they're located underneath it. So this is usually done via machine, and they have the solder paste down, and then it's saying, oh, hey, the solder paste that you should use should be kind of this right here. And then it's actually saying, hey, this is the one they're recommending. Now, it's not to say you couldn't use different solders, but this is the one they're recommending. All right, and that takes us, actually it doesn't take us through it. Sometimes they have this nice here, which they don't always have, and as a side note, they don't always have these diagrams and data sheets, but it's actually giving you a recommended PCB layout here with all of the parameters, which is actually very nice. And then in the red is the landing. So what that is that's like the size. When it says landing, that would be the actual pad stack for it. Yeah, and so that takes us through the data sheet. So, and then we got like some index and stuff. All right, so that's all this video is actually going to be here. Seems kind of like a long video just for going through a data sheet, but it's important to be able to go through these data sheets.